Okay, so we have done the graph of the sine function and the cos function. Those are called sinusoidal functions, right? Sinusoidal being that repetitive wave with characteristics of amplitude, period, median, midline, etc. They're split into 4 parts, right? They go from the midline to the maximum, back to the midline to the minimum, back to the midline, or they go from the maximum down to the midline, down to the minimum, back up to the midline, back up to the maximum, right? Each of those 4 parts will be 1/4 of the period. So as long as you can see a quarter of a cycle, then you can figure out what the period is, right? You just know, oh, that's a quarter because it went from a midline to a maximum. Okay, and I can see that, so then I know that that took place in this many theta units, or x units, or t units. So we start doing applications. A lot of the time, it's time that's on the x-axis, right? Things vary with time in a sinusoidal. Just think of temperatures, right? Starting to get colder now, and what? It's going to continue to get colder and colder. And then what? Then starts getting, midwinter, and it's the coldest, and then it starts to warm up. And it warms up through the spring and the summer, and then midsummer it's the hottest, and then it starts to cool down. That repeats. Yearly pattern, right? It repeats like this. Big hours of daylight. Right? We're getting fewer hours of daylight now, right? Also in this sinusoidal pattern. Anyways, let's go off on a tangent. I had something for this. Tangent. Where is it? There. Tangent, not this guy. That's not the tangent we want. Who is that guy? Anybody know? You're too young. Yeah, George Hamilton. Yeah, he's famous for his tan, right? Probably his skin is like leather now, probably. Anyways, use the table of values on the first page to graph y equals tan theta on the grid below. You'll have to supplement the values in the table so you can draw an accurate graph, right? Because the problem is, tangent's not limited between 1 and -1, right? But let's just sort of start tangent. So the tan of 0 is 0. Now, we have one nice number with tangent. What's the one nice number in that whole list? Well, 2 nice numbers. What are they? 3 nice numbers. One of them is 0. What's the other one? 1 and -1. Where does 1 as a y value occur? Like what value of theta? What's the first value of theta? No. Pi over 4, right? Which is how many of these ticks? How many are there? Always, almost always. 12, right? Because if there's 12, we can do pi over 2s, pi over 3s, pi over 4s, and pi over 6s, right? They all have a common denominator. The lowest common denominator is 12 for all of those guys, right? So you can do the pi over 2s. All right, so we've got 1, 2, 3 of these guys, and that gives me this nice point here. And if I go 1, 2, 3 this way, I have this nice point here. Now that allows us to, if there's a transformation to the tangent function, like some sort of a stretch, we can figure it out because we know that pi over 4 units to the right, it should be going up 1 unit. So now if all of a sudden it goes up 7 units, then we know it got stretched by a factor of 7. Now, our transformations, though, in this course are mostly sinusoidal, right? So the sine curve and the cosine, we're going to do everything to them, right? We do the whole gamut of transformations. But, But with the tangent curve and the reciprocal function, so cosecant, secant, and cotangent, which we'll get to in a few minutes, we'll limit it to maybe 1 transformation, right? Like we won't throw a whole bunch at you. Okay, so you won't really have to worry as much, but we really need to be very, very, very familiar with the sine function and the cosine function. Okay, so that we can look at any graph and say, oh, yeah, this happened, right? There was a vertical stretch by a factor of this. There was reflection in this. There was this and this. Okay, just as we've done for every other transformation. Tan and secant, cosecant, and cotangent, not so much, right? Maybe 1 transformation. Anyways, continuing on to graph. So really, I mean, the other numbers are somewhere in here, but we've got like a root 3 over 3, so we've got some other decimals. Where does it go off the graph? Where is it undefined? And so at pi over 2, it's infinity, right? Which means, and if you think about that, I mean, what is tan? Well, you know, tan is y over x. And if x is 0, then I've got 1 divided by 0, which is undefined. Okay, and you can't do that. So we have an asymptote at pi over 2. And the other place that x goes to 0 is at negative pi over 2, or 3 pi over 2. So 3 pi over 2, we get an asymptote. And at negative 3 pi over 2, which is really just pi over 2, 6. Okay, and we've got these 3 points going on, and we can graph some other points, and you're going to have to throw in some other stuff, so you might have to do, okay, what's like pi over 12? What's pi over 6? That's in my table. What's 5 pi over 12? What is it as I get close to pi over 2? Like just a little bit less than that. So if I do the tangent of pi over 2 minus 0.1 or something, or the tangent of pi over 2 minus 0.01, what kind of values do I get? Okay, so if I'm going to use this, I better flip it back to radians. So always watch the mode you're in. I think in general, they don't put answers on the diploma that's your calculator's in the wrong mode. Right, so they won't ask you a question, you should be in radians, you're in degrees, and there's the answer, but that could happen. Okay. But if it's numeric response and you're in the wrong mode, then you're going to get an answer, and hopefully you'll recognize that doesn't seem to make sense. Okay, and check your mode. So check your mode at all times. So okay, oops, hold on 1 second. There we go. Okay, so let's go tan. So if I tan pi divided by 2 minus 0.1. So we just say close to pi over 2. So it's like almost 10. Right? So when I'm a tenth of a unit away, we're going to be like here. Well, what happens if we get closer? So let's do the same deal. Only let's go minus 0.01. 99. Okay, so we know it's getting really, really big, right? And what's happening is we get close to negative pi over 2, but this time instead of subtracting, I'm going to add 0.1, right? So let's go back here and do the tan of negative, so I'm going to insert a negative. Now if I do minus 0.01, I'm going to be on the other side, because I don't want to do that, right? So I'm going to do plus. Negative 99. Okay, so here's what the tan curve looks like. I'm lazy, so I'm just going to... Okay, little arrows there. And what happens at pi? What's the tan of pi? Or negative pi? Yeah, 0. Or what's the tan of 2 pi? Or negative 2 pi? Okay, and then if I go 1, 2, 3, 1, and 1, 2, 3, negative 1, we've got the same deal going on. And then over here, well, we're just going to see this bit of it. Kind of, let's redo that. So 1, 2, 3, that'll be negative 1. Okay. And over here, we're just going to see this part of it, right? So, tangent graph. Tangent graph. All right, needs a couple minutes. Let me pause this while you copy. Is the graph periodic? Yeah. Does it repeat? Yeah. Yes. What's the period? How long does it take to go through a complete cycle? 1 pi. So the period is pi. It's different, right? Sinusoidal, the sine, cosine, those are 2 pi. Why is the graph y equals tan theta not sinusoidal? Not a wave. Okay, it's not a wave. not wave-shaped. And let's also add no max or min value. What's the maximum value? There isn't one, it's infinity, right? It goes forever. So no maximum or minimum value. Value. Does it have an amplitude? No. No, because there's no max or min, right? An amplitude is defined as half the distance between the maximum and the minimum, right? Or the distance from the median to the max. So no amplitude. So no max or min means no amplitude. That doesn't mean that I can't necessarily throw a number in front. Like we're going to be looking at stuff like y equals 2 sine theta and then say the amplitude is 2. Yeah.
There's an equal amount of positive y values as the y values.
Yes. There are equally, infinitely many.
So would the just be less zero?
Well, no, wouldn't it be like 2 infinity divided by 2, which is just 1 infinity, except there's really no such thing because infinity is infinity. So you can't double it and then divide it by 2 and say, because it's still infinitely large. Yeah, so we can't do it. There's no amplitude. Right. So we can't take it, we can't split infinitives, nor can we split infinities. The range, what's the range? What is it? Y belongs to reals, or you could go R colon and then negative infinity comma positive infinity. Right? So the range is going to cover all y values, right? The graph has vertical asymptotes, where cos theta is, remember cos theta is x, and x is 3. But cos theta is equal to what? Not theta, okay? Start getting into this. I know this is a tough thing. This is what happens. I asked where cos theta is pi over 2. No, it's where theta is pi over 2. It's where cos theta is 0. So don't mix up theta and cos theta, right? This is where cos theta is equal to 0. Now, the general expression for the vertical asymptote, now what are the values of theta? N pi. Okay, so the general expression. So the asymptotes for theta is equal to n pi. What am I going to say next? Okay, it's where n belongs to the integers, right? But in multiple pi. Where there's a vertical asymptote is at n pi. Is it? No, wait, that's not where the asymptotes are. Why are you lying to me? Go back. I can't see them. The asymptote's at pi over 2, and then how do you get here? Oh, why do I listen to you guys? Where's the first one? And how far apart are they? Okay, so it's pi over 2. So what we do, if we're listing something like this, like a general thing, go for the first positive one. Theta is pi over 2. And then how far apart are they? They're pi units apart. So it's theta over 2 plus n pi. So that's where the asymptotes are. What does that mean the domain is then? Yeah, so they're all theta such that theta is not equal to, right? So the asymptote, that's where it is equal to. The domain says you're not allowed to be equal to. So theta is not equal to pi over 2 plus n pi, where n belongs to the integers. Okay. Now, I listened to you on this one. General expression for the theta intercepts. Where do we intercept theta? I'm going back to the graph. I don't trust you anymore. You've lost me. So theta intercepts are where? N pi. Now it's n pi. So theta intercepts are where theta is equal to n pi and n belongs to the integers. What's the y-intercept? 0, right? Y-intercept is at 0. And it's happy to be there. That's also, how can you tell if it's a humorless one. How can you tell if it's been shifted, right? I mean, what do the stretches do? And the reflections, they don't do anything to a point that's at 0, 0, right? So think about sine. The sine function goes through 0, 0. So what's the only way the sine function, what's the only way 0, 0 goes somewhere? You got to move it horizontal. Translations, right? It's horizontal and vertical. The only way the tan function goes somewhere, at least this point, is under a translation, not under a stretch, not under any reflection. This doesn't go anywhere, right? Like 0's on every line of stretch or reflection. It's on the y-axis, the x-axis, and the line y equals x. So a stretch, nothing. Reflection, nothing. The only way this point goes anywhere, translations, right? So if you can identify this point, which is probably, it's easy to find, right? It's kind of the point of inflection where this changes direction. Remember we did that with some polynomial? This is not a cubic, however. Graphs of the reciprocal functions. Okay, so we're going to do cosecant and secant and cotangent. So cosecant is the blank of the function what? It's the reciprocal of the function sine. Why sine? Because each pair only has one co, right? So cosecant is the reciprocal of sine. Secant is reciprocal of cos, and cotangent, the only one that actually really makes any sense, is the reciprocal of tan. It's like, why isn't it like sine, cosine, and then, I don't know, secant, cosecant, the cosine function should be called secant, but it's not. As in the previous unit, and in Math 20-1, we do reciprocals of functions, right? If only we could remember how. So, graph of sine theta, draw the graph of cosecant theta. Okay, when you're drawing a reciprocal, what's the first thing you look for? You find the what of the original function? Find the zeros, and what do you do there? You draw a vertical asymptote. So, we get the zeros of the original function, the reciprocal function, we're going to be looking at 1 over 0, which is undefined, you can't do that, so we've got an asymptote. So everywhere the original function. Okay, what else do we do? Want to draw a reciprocal, what do you do? Sorry, what's the next thing you do? Invariant points, where are they? So you go along the line y equals 1, and you go along the line y equals -1, and you mark those points as invariant. Okay, so we find the original function, zeros of the original function will be asymptotes of the reciprocal. The ones and negative ones of the original function will be the invariant points. There'll be 1, -1. Okay, this is going down, getting smaller. What's this going to do? It's going to go up. This is going down. This is going up. Okay, so that's the reciprocal of sine, which is cosecant. Okay, so that's what the cosecant function looks like. Ask any questions here? Nope. Okay, so I want you to do the reciprocal of cosine, which is at the bottom of the page. Or for me, the next page. Graph of cos theta is shown. Graph secant theta. I'll pause this and Okay, so here are the zeros of the cosine function. These will be asymptotes for secant. Here are the invariant points at 1 and -1. So this guy's going to go here, and here. This guy's going to go up here and start to go up there. This guy's going to go up and up and down and down and up. A little bit up. Okay. So if you want to know who's who, right? Like, I mean, I know the sine function way better than the cos. I know sine and cos way better than I know secant and cosecant. But all I really got to do is think about, well, the invariant point is where it's 1, and sine is 1 over here. So if I see one of these guys and it's like over here, then I say, oh, that's inverse of sine, because that's where sine is 1. And here's cos is 1 here. Okay, then this is the invariant of, or sorry, that's the invariant point for secant, right? So if you're asked to just state, is this a cosecant or is this a secant, just say, where is the invariant point? Okay, sketched. 2 pages to go. And if there's time, maybe you can see your quizzes, the multiple choice part you never saw yet. What are the similarities and differences between the two graphs? Same shape, right? Translate, yeah, one is just translation how much? Horizontally pi over 2 units, okay? So they're the same shape. What else? They have no x-intercepts, right? They do not intercept the x-axis. They have the same range, right? They have the same range. They do not have the same domain. That's a difference, right? They do not have the same domain. But I mean, let's throw this in. One graph is a horizontal translation. Pi over 2 units of the other graph. Okay, and I'm not going to specify which is which. I mean, you can say secant is the horizontal translation pi over 2 units to the whatever, the cosecant of the cosecant graph. But just say the horizontal translation. If you move one graph pi over 2 units, you'll get the other graph. Okay, or else they do not have the same domain. So that's a difference. Okay, they have vertical asymptotes, right? A general expression for the asymptotes. Okay, so the asymptotes of cosecant. Cosecant is the reciprocal of who? Sine. It's going to be an asymptote when sine is equal to, when sine theta is 0, which occurs at n pi, right? I'm not relying on you anymore, I'm sorry. So theta is equal to n pi, where n. So then the secant is the reciprocal of cosine, so its asymptotes will be where cosine is 0, which is? No, it's not n pi over 2. Why would you say that? It's pi over 2 plus n pi. I mean, we can say n pi over 2. There is meaning to that. It's just not meaningful in this particular case. N pi over 2 just means every half pi something's happening, right? 0, half pi, 1 pi, 2, 1/2 pi, 2 pi, 3 pi. Okay, and there might be something happening there, but not in this case. So what's the domain? What do we write? The exact same thing, only with not equal to. Okay, we'll throw in some set notation. So the set of all theta such that theta is not equal. So the asymptotes, this is where asymptotes are at n pi. The domain is not at n pi, right? The asymptote is n pi. The domain is not n pi. The domain here is theta is not equal to pi over 2 plus n pi. What's the range? What can you say about y? It's 4. What's the first thing you say? Greater than or equal to 1, or it's less than or equal to negative 1? Okay, I'll go you one better. The absolute value of y is greater than or equal to 1. Okay, we'll say that. So such that y is greater than or equal to 1, or y is less than or equal to negative 1. Or you could just say the absolute value of y is greater than or equal to 1. That works until you stretch it and then translate it, right? Because then you have to go with the first domain. Or just translate. If I translated it, I can't say the absolute value of y is greater than or equal to 1 anymore. Like if I moved it up 1 unit, it's greater than or equal to 2 and less than or equal to 0. So, be able to state it both ways. This is just the fancy way. This is highfalutin, right? It's like, the magnitude just says the magnitude. Just says the size of it has to be bigger than 1, whether it's positive or negative. Sorry, bigger than or equal to, right? Because we say bigger than or equal to a lot. Greater than or equal to. What's next? 29. The length of one complete cycle. So how long does it take to do a complete cycle? Really? So what would define a complete cycle? You'd need full up, full down, right? 2 pi. Okay. You got to cover all the values that can be covered. We could do that in 2 pi, right? Okay. You got a set of up, and you got to set it down, right? And this is 2 pi. Okay. That's complete cycle. Complete cycle goes through all possible values. Therefore, the period. Okay, so the period is 2 pi. Are they the same answers? They are. 2 pi. So period is the length or the amount of time. A lot of times say time because a lot of times this is associated with time. A sine or a cos. Why are there no theta intercepts? Yeah, there's a reciprocal function, right? Like cosecant theta is 1 over sine theta. The only way that expression becomes 0 is if the numerator becomes 0. Okay? We cannot make the numerator 0. Right? So there's no theta intercept, right? So this cannot equal 0, right? Since the numerator can't be 0. Since numerator can't be 0. And then same reasoning for secant, right? Only we write 1 over cos theta. And we say, well, that can't be 0 either. Same reason, right? The numerator is 1. You cannot make that expression equal to 0. Okay, if you want a division expression be equal to 0, you have to get the numerator to 0. Y-intercept of cosecant. Really? It went through 0? So what's the y-intercept? There isn't one. Does not exist. Right? There's a vertical asymptote on the y-axis, so there is no y-intercept, right? You can't get there. What's the y-intercept of secant? 1. Right? Secant reciprocal of cos, the cos of 0 is 1. Cosecant reciprocal of sine, the sine of 0 is 0. The reciprocal of that does not exist. Right? Can't do that. Is there more? Tan. Okay, so you want to graph cotan. Okay, you're going to have to shrink this a bit to graph cotan. What's the first thing we look for? The zeros. What do we do with the zeros? We draw asymptotes. Okay, I'm just going to knock this down to like 100%. Okay, so zeros are for asymptotes. What's the next thing we look for? Ones and minus ones, because those are the what? Invariant points. I'm still drawing an asymptote. Okay, so 1, 1, 1, 1, negative 1, negative 1. Here's a question for you. On the tan function, which is shown, what do you think happens when there's an asymptote on the original function? What's in the reciprocal function? No. Okay, on the tan function, we sketched asymptotes where? Where the original function is 0. So if a reciprocal function has an asymptote, what does the original function have? They're paired. Yeah, the next intercept is a 0, right? If you have an asymptote on this curve, which occurs here, then the reciprocal curve has a 0, right? Because if you took the reciprocal of this curve, you'd be drawing an asymptote right there. So everywhere there's an asymptote, 1, 2, 3, 4, 5, 6, there's a 0. 1, 2, 3, 4, 5, 6. Okay. And then shape-wise, these guys are going down and getting small, so what are these guys doing? They're climbing and going up. These guys are going down and getting small negatives, so they're going to become large negatives, and then we're just going to kind of join this up. And then lather, rinse, repeat. Right? And one last one. Okay, there you go. And we've added one thing to our arsenal of reciprocal drawing, which is if the original function has an asymptote, then we know the reciprocal function has a 0 at that point. So again, on tangent, secant, cosecant, and cotangent, we're going to do not a whole bunch with transformations, like maybe one thing. Cotan has vertical asymptotes at values of theta, where sine theta is equal to, what's sine theta equal to? 0. The general expression for the vertical asymptotes of cotan theta, that's where sine theta is 0, which by now we're starting to know is n pi. And so the domain is, I should say theta equals n pi, right? So what's the domain? Instead of writing is equal to, we say is not equal to. Right? Where the asymptotes are is where the domain is not. Right? So set of all theta such that theta is not equal to n pi. Range? I shouldn't write that, it'd be consistent. Period? It's the reciprocal of tan, so it's got to have the same period, right? So what's period? Pi. You will come to know this. General expression for the theta intercepts. Let's go look at it. Where are they? Looks like pi over 2 plus n pi, right? Because if you think about it, cotan is y over x. But cotan is x over y, which is cos theta over sine theta. So it'll be 0 when cos theta is 0, which by now we're starting to figure out is pi over 2 plus n pi, and sine theta is 0 at n pi. Okay, so this theta intercept, theta is equal to pi over 2 plus n pi. And is there a y-intercept? No, there's vertical asymptote on the y-axis, right? So it has no y-intercept. Is that it? It is.